Now, one of the other things that's really important to talk about in terms of implicit differentiations is its application, and that's when we talk about related rates like we are here. And all related rates is just an application of implicit differentiation. Right? It's important to think about, we talk about deriving something as being a measure of the slope, and slope, of course, as we know, is just a measure of rate of change. So this is really starting to use calculus as it was meant to be used, to start to measure the way um, something is changing, an action or an activity is changing. The biggest piece of advice I can offer is that these are word problems. So as with any word problem, it's crucial to isolate what you're given. These in particular can often be assisted by drawing a diagram to help organize your information and figure out how best to attack the problem. So in my first example here, right, air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. So remember that IB will often write this, instead of with the ratio, they'll write this as centimeters cubed per seconds to the negative 1. Don't ask me why, they just do, just be aware of it. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So let's figure out our given information first. We have some kind of a spherical balloon, and the way the spherical balloon works, its volume increases at a rate of 100 centimeters cubed per second. All right, so that's important. So what are we given? We're given a spherical balloon. And we know that its volume increases at a rate of 100 centimeters cubed per second, right? So this is a rate of change with respect to time. One thing I like to do as I come up with information is to start putting it in calculus terms. So one of the kind of calculus ways we could write this is if the rate of change of volume with respect to time, which is what dV by dt means, the change in volume with respect to time is 100. Right? 100, and if we wanted the units on it, we could do that. How did I figure that out? Well, I kind of looked at my units, right? Centimeters cubed is a measure of volume. Seconds, of course, a measure of time. And just to be abundantly clear, right, we can read this as a change in volume. I'll use WRT for with respect to time. That's all that's saying. Of course, I'm given volume, right? I know volume. So how do we deal with this? Well, the other thing we know is that the volume of a sphere is 4/3 pi r cubed. So both of these may come in handy. We don't know yet if they're going to help for sure, but it's important to look at it just in case. It's better to have it on the paper and not use it than not have it on the paper and then realize you need it later on. Let's head back into the problem. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So a couple other pieces of information I know that the diameter, keep my colors the same, my diameter is 50 centimeters, and I'm being asked to find how fast, so I'll say the rate of change of radius. So actually, we're going to work this backwards. Let's put that into calculus terms first. So this is the change in radius with respect to time, dr by dt. Again, using logical variables. The fact that they gave you the diameter should raise all kinds of red flags. Right? The fact that they gave you diameter should be careful. Right? This is meant to throw you off. Because what's important when we're talking about calculations with spheres and circles is the radius. So the first thing you should do is calculate the radius and convert this to the more helpful piece of information. The radius is 25 centimeters, just half the diameter. anytime, read the problem carefully. That's all it comes down to, right? Read carefully. Right? They don't give you anything to do with the diameter here in the problem. So I should convert to the thing that I actually am given to work with, which is the radius. So I've got all of my information lined up. It's nice and organized. I color-coded, but I realize you might not have that luxury. The other thing I might want to do, the other thing you can consider if it helps, is to actually draw out the problem. So maybe here is my balloon. It is a sphere, which means it has a radius. And as we've learned, that radius is 25 centimeters. And the other thing we were told in the problem that we need to figure out, right, is how fast is that radius changing? We know that its volume, well, we don't know its volume, but we know its volume is represented by 4/3 pi r squared. And the other thing that we know about the volume is that, we know that the volume is changing at a rate of 100 centimeters cubed per second. In this problem, maybe it's not particularly helpful, but in other problems it might be more helpful. It's just a good habit to get into. Well, so now we need to start working. So that was all set up. Now it's time to work. The key with related rates. Is that you're usually given a formula to work with, or it's hinted at. So what that means is either they explicitly give you the formula, or in this case, we know, well, they're talking about volume, so maybe that's important. Maybe that's important to work with. So we should follow our instincts. Trust your gut. You are coming up on the end of your first year in IBHL. You've developed great mathematical intuition. You should use it. So my mathematical intuition tells me, trust my gut. I realize now that this should say cubed. I have this formula. I should do something with it. I'm going to look at this and say, well, what do I need to do with it? I need to introduce two things. Maybe I'll put this off to the side. I need to introduce two things. I need to introduce a dv by dt, and I need to introduce a dr by dt, because I'm given these things, or I'm being asked to solve these things. So I should be able to use everything I'm given. How do I do that? Well, I'm deriving by something other than a variable that I have already. So the way I'm going to do that is to derive implicitly. So we'll just put a note here to say use implicit. So I'm going to derive everything here with respect to time, because everything I'm being asked to work with involves time. It's a rate of change. Rates of change happen over time. I'm deriving with respect to time. So just like we learned in the first video, anytime I'm deriving here with respect to something other than the variable that I'm given, I need to include that little extra differential as a correction. So v clearly doesn't match, so we're going to call this dv by dt. And then r clearly doesn't match, so I'm just going to derive like normal and correct for it later. So I'll use my power rule, right? This becomes 4/3 pi, that's just a constant, times 3r squared dr by dt. And you can see that I've introduced those two differentials that I needed to introduce. So I'm just actually going to simplify this a little bit more first. This will just become 4 pi r squared dr by dt. If you look, I have everything that I was given that I can finally play with, or that I was being asked to solve for, right? Remember that I'm being asked to solve for dr by dt, and I know the rate of change in volume, and I know what my radius is. So I can just plug those in, right? dV by dt is 100. 25, my radius. We can figure out what that is squared later. And I'm solving for my dr dt. So I've now got all of the pieces that I need in order to solve this, right? This just got a whole lot easier. For our sake, let's just simplify the right-hand side. So we'll leave it in terms of pi for now, I guess. 4 times 25 squared is 2,500. So this is going to be 100 equals 2,500 pi dr by dt. Which is great. I'm just going to solve for dr by dt, so divided by 2,500 pi, and I get approximately 0.126. And of course, my units are important. My units are centimeters. Remember, I'm sticking with that IB rule of 3 significant figures. Always important in application problems with rounding. So this is kind of the overview, right? I'm going to start, if I were to maybe come up with a process here, right? I'm going to start by isolating my given information and my goal, right? My given information, my goal. If I want to, maybe optional, I can draw a diagram, but I would recommend it. I want to identify a formula I can work with. And usually then that's going to involve some sort of implicit differentiation. From that point on, it's just using your good algebra skills to solve for the missing variable. Check your answer at the end. Do I have 3 sig figs if necessary? And do I have units at the end? Both very important things to consider. So let's try one more. Now that I maybe don't have to talk through so much, hopefully this will go a little bit faster. So we're going to start same way as before. Let's just isolate our information. I have a 10-foot long ladder, and it's resting against a vertical wall. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. And I want to know how fast the top of the ladder is sliding down the wall at the moment that the bottom of the ladder is 6 feet away from the wall. This is a problem with a lot of information. This is a problem that's much better to start with drawing a picture, but let's actually start by isolating it just to keep our process the same for now. We know that we have a 10-foot long ladder. We know that the wall is vertical. We know that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. Normally here I would convert this into calculus language, but it's kind of hard to visualize right now without a picture. I'm also going to want to know something to do with when the bottom is 6 feet away from the wall. And at that moment, my goal is to find the rate at which the top of the ladder is sliding down the wall. So again, not super helpful here like it was before, but with the ladder problem, these are both of these are pretty quintessential problems. This ladder problem specifically. With this ladder problem, so maybe I've got, let's get colorful here. Maybe I've got my wall, right here is my wall. And here is the ground. And I've got my ladder. So here is my ladder. So what do we know? We know that the ladder is 10 feet long. Actually, before we even do that, what do we notice? We notice that we've got a right triangle. That's going to be useful. We know that this ladder is 10 feet long. Well, what else is this ladder? This ladder is the hypotenuse of our right triangle. So in terms of x, y, and z, actually I'll do that. I'll call them x, y, and z, which is great. And then just as before, we need to know some rates of change, right? I know that the bottom is sliding away from the wall at a rate of 1 foot per second. So the rate of change in the position of the bottom of the ladder, dy, over time, dt, is 1 foot per second. I don't know how fast the top of the ladder is sliding down the wall. But that's okay because I'm being asked to solve for it. And I'm doing this at the instant when the bottom of the ladder is 6 feet from the wall. So for this purpose, we're going to assume that y is equal to 6. Let me keep my colors the same. So we're going to assume that it's equal to 6. Now you might notice that there's something missing here, right? What is dz by dt, right? This is the one part I don't have, right? The rate and change in the length of the ladder with respect to time. Well, the ladder is a fixed 10 feet long, right? This isn't one of those extendable ladders that suddenly, shrink in on itself. So is the rate of the ladder's length changing at all? No, it's not. So dz by dt is 0. In this case, it's a constant. That's kind of an important piece. So as before, I've drawn my picture, and the next thing to do normally would be to figure out my formula. Well, I'm not explicitly given one. There's not one that's even really being hinted at, which is where the diagram came in handy. From the diagram, remember that we said that I have a right triangle. What formula do I know that uses a right triangle famously, and that would be the Pythagorean Theorem. So, using my good instincts, and with the latter problem, you'll always use the Pythagorean Theorem, but using my good intuition, maybe I should consider using the Pythagorean Theorem. And of course, the next thing to do was to derive implicitly. So I'm going to take this entire thing. For the sake of space, I'm just going to write it over here. And this is going to give me 2x dx by dt, 2y dy by dt, and 2z dz by dt. This is where we plug in all the things that we know. Keep my colors the same. We don't know what x is. We'll come back to that. We don't know what x is. We don't even know what the rate of change in x is. But we know that at this moment y is 6 and dy by dt is 1. We know that z is 10 and dz by dt is 0. I'm off to a great start here, right? Oops, dx by dt plus 12 equals 0. But I realize if I go to solve this, I'm stuck because I don't know what x is. I can figure out what x is. I'm given two sides of a right triangle. I can use the Pythagorean theorem. So I should do that. And really, I should have done it kind of right away. But I'll be the first to admit that it maybe slipped my mind just a little bit because I was focused on getting through this problem. But we can really quickly see that x is 8. You might be saying, what about negative 8? I can't have a negative distance, so just the positive one. So x is 8. That's going to go right into my my working so far. I have dx by dt equals negative 12 over 16. Now, just for the sake of consistency, let's put this in terms of a fraction. I get 0.75. Using my units, feet per second. You might be wondering about this negative here. That's just to indicate the fact that we are sliding down the wall. kind of defining down as my negative direction. It just means that we're sliding down the wall. So to answer my question, how fast are we sliding down the wall? Depending on how you word it, I guess maybe you could even just say 0.75 feet per second. But there's our process again, right? Isolate your given and your goal. Well, there it is. Draw a diagram. In this case, the diagram was crucial, right? We wanted to then identify a formula and derive implicitly. So here was our formula. Here is our implicit differentiation. We're using our good old algebra skills here. And of course, checking at the end, do I have 3 sig figs? I don't really need them because my answer is exact. Do I have units? Yes, I do.